Hello, welcome. So today we're very happy to have Matt Baker here, who will tell us about card shuffling, necklaces, and the Mandelbrot set. And how would you like people to ask questions?
Oh, I think I might not be able to monitor the chat, so they can just interrupt or they can post a comment, and then if you, Simon, can monitor the chat, you let me know if there's something time sensitive or we can save till the end.
Sure, I can do that. Okay, so yeah, you can go ahead.
Okay, well, welcome everyone. My name is Matt Baker. I'm a math professor at Georgia Tech and also a professional magician. And I wanted to focus this talk on some combination of these two things. Namely, I'm going to start out with a magic trick, and we'll actually teach the magic trick and some of the math behind it. And then I'm going to talk about a math research project that was inspired by this magic trick and which led to a published paper that I wrote with three high school students. And along the way, we'll learn about fractals and the Mandelbrot set and some interesting things about
Porta.
polynomials.
Yeah, that's good.
Okay, and someone needs to mute, I think. Okay, so let's get started with the magic trick. I'm going to need a volunteer to help me out with this. Is there anyone that's
I would like to, sir.
okay? We have Luke, I believe. Do you want to turn your camera on if Luke is indeed the one that is volunteering?
Yes, of course. Just give me a second.
Sure. All right, so while we're waiting, I have a deck of cards here, and we are
इसका
going
मेरे को नहीं पेंट करना
to play a game.
और उसका
Okay, are we ready? All right. So Luke, do you enjoy gambling games?
Yeah, a little bit.
Yeah. Okay. Then you'll be perfect for this. Um, so we're gonna bet some money on the outcome of a card game, but don't worry, it's going to be extremely fair. Okay.
Okay, I believe you.
So let's see. I think maybe we bet $1 a hand. And what's going to happen is this. If so, we're gonna deal the cards out into pairs, and if they have different colors like this, then I win. But if they're the same color, which could be both red or both black, then you win. So you actually have two ways of winning, Luke, both red or both black. I only have one way of winning, which is if they're different. So your odds are better. Uh,
Okay.
so
Okay.
Luke doesn't seem to be buying this at all. All right, usually I give myself 2-to-1 odds. So like you would pay me $2 when I win, and I would pay you $1 when you win. But I think some of you, maybe all of you, are budding mathematicians and probably already see through this little charade. Okay, so that's actually not a fair. That wouldn't be fair if it was 2-to-1 because the odds are actually 50-50, right? The odds of getting different colors are the same as the odds of getting the same color. So I'll be fair. I promised I would make this fair. So we're going to make it 50-50. So if it's different colors, you give me $1. And if they're the same color, I give you $1. Okay?
All right.
And I accept PayPal, Venmo, and most
Really?
major cards.
Okay.
All right. So here we go. Now, it's very important, though, since we don't know each other and we need to establish trust here. Do you promise to abide by the rules of the game?
Yes.
Okay, great. So everybody heard that. Luke just promised to abide by the rules of the game. Now, here's a pro tip for you, Luke. Never agree before you know what the rules are to abide by the rules of the game because he
Okay.
agreed before I even explained them. So I, for example, don't even have to shuffle the cards now, right? Because I didn't say that was part of it. And I could have just set up the cards in advance in a way that would make me win. But then I would look like a jerk, and that's not worth $26 to me. So tell you what, I'm going to be fair. I'm actually going to allow us to shuffle the cards. Now, if you were here in person, I would literally let you do the shuffling. But since you're not, I'll do the shuffling for you, but you can see that it's very fair. Okay, so here I'll shuffle them this way because I don't want you to think I'm doing some funny magician shuffle. So we'll literally just smush them into each other like this, okay? And I think that's pretty fair. And we're ready to go.
Would you like to shuffle a little bit more?
No, I think one shuffle's probably
Okay,
good.
yeah.
So let's see. First two cards. All right. Well, that was probably lucky. So that's 1 point for me. Somebody keep track of the score. Okay, there's 2 points for me. Oh, wow. 3-0. Okay. 4-0. There's 5. Oh. Okay. That wasn't supposed to happen.
What do you mean?
Let's do this one because I'm going to explain this. So what's supposed to happen is that I'm supposed to win every time.
You said you're a professional magician?
Semi-professional, apparently.
Oh, okay, okay.
Let's try this one more time. Yeah, I mean it's just a fun demonstration.
Right.
I don't know what happened there, but let's do it again.
So why? Okay. What are those two piles there?
I'm resetting and showing you basically how the trick is done as we're doing it because it didn't work right. And I want you to see how it works. Okay, so it should be reset. And let me just walk you through what we tried to do again. Okay, so, oh yeah, I know exactly what I did. Sorry, I haven't done this in a little while. So I'm going to shuffle the cards like this again, push them into each other. And now we're ready to go. Okay, so here we go. Everybody keep score. There's 1, 2, 3. They're all different still. 4, 5, 6, 7, 8-0. There's 9, 10, 11, 12, 13, 14, 15, 16. Luke, you're going to win one of these days, I'm sure. 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. Okay. So that's how the demonstration is supposed to work.
It's just the luck of the draw, you know?
Thank you for playing, but you know what? Since I had to cheat there, I won't make you pay up, all right?
Okay, thank you.
We'll just call it even. All right, now let me explain. So it's a cool trick that you all will be immediately able to go home and show your friends and family. And it's based on a really cool math principle called the Gilbreth principle, okay? And here's how it works. You secretly, I did it not so secretly, divide the deck into reds and blacks at the beginning. Okay, so I'll just go through that quickly so I can reset. And I won't do the whole deck. Well, I may as well. All right, and then I'm going to shuffle them. I'm going to do a perfect shuffle so that they're alternating reds and blacks. That's actually the initial setup. Now, if you can't do a perfect shuffle, then just deal them into just set it up so that they alternate red black. I just find it faster to do red black and then do a perfect shuffle like this. Okay, and now the cards are alternating reds and blacks. But again, you just set that up beforehand however you like. Now, here's the crazy thing. So this is the initial setup. Crazy thing is, if you shuffle this just one time, oh yeah, someone asked how much practice does that take? A lot. That's a separate story. We can go into that at the end if you want, but that's not easy to do. But luckily, it's not needed for this trick. So when the trick starts, now what I forgot, I just got confused about something. You need to cut them so that the faces are different. I actually cut them so they were the same. And I don't know why. Yeah, so no, I didn't make a mistake with the perfect shuffle. The mistake was this. I cut off center and I had red and red on the bottom. And I actually wanted red and black on the bottom. Okay, so when you cut it, you need different colors. That was my only mistake. Then if Luke was here, I could. Oh, no, he said, are there? No, there's 52 cards here. So you have to cut it off center, right? If I cut it evenly, then I'd have the same color on the bottoms. But you want to cut it off center so that there's different colors on the bottoms. Okay. And now you let the participant shuffle. I'll do a normal shuffle here. I just did the other shuffle because it makes it more clear that they're really being mixed. But this is not a perfect shuffle. This is just any spectator shuffle. However they shuffle, they really riffle shuffle it and really put them together. And the theorem is that if we go through the cards in pairs, there will always be exactly one red and one black in each pair, even though we just shuffled them. They don't occur in the same order, right? Here's black and red, and then red and black. There's red, black, but there's a black, red. So they don't occur in the same order each time, but they will always be paired up red, black. Now let's look quickly as to why this is true, although it's sort of a fun exercise or homework problem to figure this out for yourself, but I'll sort of give you a hint here. Okay, so let's say we have red, black, red, black, red, black, and red, black. So here's just an 8-card stack to give you the idea of what's happening. So we cut it off center, right, like that. So I have 3 here, 5 here. So now there's different colors on the bottom. And we shuffle them together however we like. But here's what's happening in that shuffle. One of these 2 cards falls first. Let's say it's this one. So this card gets released first. Now the next one of my 2 hands is going to release the next card. But look, it doesn't matter. It's either red or red. So if the first one's black, the next one has got to be red. And now we're back in the same situation we were before. Each packet alternates colors, okay? And we've got 1 red and 1 black on the bottom. And let's say this time a black or a red card falls first. Now, whichever card goes next, it's black or black, and it doesn't matter. So maybe it's this black. And now again, we're in the same situation. One of these 2 will fall first. Maybe it's this red. And then, oh, sorry, I took that from the wrong place. Anyway, it works. Each in sort of by induction, after whichever card falls first, black or red, if it's black, the next card you'll have a choice of 2 reds. If it's red, the next card you'll have a choice of 2 blacks. And so they always pair up. I hope that makes sense. We can discuss more at the end if people still have questions about why that works. But it's a really neat math principle that you can base some amazing magic tricks on. Okay, that was just a quick demo. Now for the rest of the talk, I would like to actually talk about a theorem that came out of thinking about this kind of mathematics or this kind of shuffling. Okay. So let me share my screen because I have slides. Okay, I hope everyone can see that. And I just have to figure out how to full screen it. Here we go. Here we go. All right. You can see that, right?
Yep.
Great. Okay, so here's a summary of what we just talked about, the Gilbreth principle. Begin with a deck of cards in alternating red-black order. Cut the cards into 2 halves, making sure the bottom cards of the 2 halves are different. That's the key. Riffle shuffle the 2 halves together. Theorem, if you now deal the cards 2 at a time, each pair will consist of exactly one red card and one black card. And I sketched the proof of this for you. Now, I want to talk about something that Graham and Diaconis in their book Magical Mathematics call the ultimate Gilbert principle. Okay, so what is the ultimate Gilbert principle? It says, suppose we have a deck of n cards numbered 1 through n, stacked face down in numerical order. Okay, so we have card 1, card 2, card 3, etc. This is going to generalize the red and black idea. And it works for any number of cards. Okay, so what you do is you deal as many cards as you like into a face down pile on the table. And then you riffle shuffle the 2 remaining packets together. So it's the same thing I did before, except we have to reverse one of the 2 halves. Now, in the trick I did, it doesn't matter if you reverse the top half or not. By construction, the first half, the top half that I'm cutting off, starts with, say, a red card and ends with a red card because I've cut it off center. And it alternates red-black. So if I reverse it, it will be exactly the same. It'll still alternate red-black in the same pattern. So with just 2 colors, you cut them in the right way. You don't have to do the reversing part. But the general principle is you start with a deck and you reverse the top K cards, and then you shuffle the rest together. Okay, now once you've done that, once you've reverse counted some cards from the top and shuffled together, now you take any number of cards from the top of the shuffled deck. And here's the theorem. The cards that you just took can be rearranged to form a consecutive block of numbers. So maybe it goes 5, 7, 8, 6, 9, and you can rearrange it to form 5, 6, 7, 8, 9. So let me show you an example. Well, first, let me give you a definition, and then you'll see an example. So a permutation is the mathematician's name for a rearrangement, right? The mathematically precise definition, which you may or may not understand, is that it's a one-to-one and onto function from the set 1 through n to itself. But in practice, it just means a rearrangement. So for example, here's a permutation at the bottom. It takes 1 to 3. So I'm rearranging 1, 2, 3, 4, 5, 6 as 3, 1, 4, 2, 6, 5. So it's just a scrambling. But I think of it as a function that sends 1 to 3, 2 to 1, 3 to 4, 4 to 2, 5 to 6, and 6 to 5. Okay, and mathematicians also often call permutations by Greek letters like sigma. So that's how we talk about permutations. And a shuffle is a specific kind of permutation, right? It's a specific way of rearranging the deck into a new order. So I want to talk about which permutations arise in that way. So suppose sigma is some permutation of 1 through n. We'll call it a Gilbert permutation if for each j, the first j values can be rearranged to form a consecutive block. So it's just what I was talking about before. So for example, if I rearrange the deck that starts out in the order 1 through 6 so that it's now in the order 3, 2, 4, 5, 1, 6, this is a Gilbert permutation because the first 2 cards are 3 and 2, and that's a consecutive block. Then 3, 2, 4, that can be rearranged to form the consecutive block 2, 3, 4. And then we add a 5, so we have 2, 3, 4, 5. Then we have a 1, so it's 1, 2, 3, 4, 5. And finally a 6, and we have 1, 2, 3, 4, 5, 6. I hope that makes sense. So the first j cards in the shuffled deck always form a consecutive block after rearranging. So the theorem one can prove, it's not too hard, is that if you do this, then you get some if you do the Gilbert procedure, you reverse the top K cards, and then you shuffle them into the remaining cards. the permutations you can get in that way are precisely the Gilbreth permutations.
Excuse me, I have a question.
Yeah.
So it's saying it's Gilbreth if a permutation can be rearranged to form a consecutive block.
If the first J cards can be rearranged to form a consecutive block. So let's say my cards are labeled 1 through 6, and after I shuffle them, they're in the order 3, 2, 4, 5, 1, 6. The key property this has is that the top K cards for any K, here's K equals 4, form a consecutive block after you rearrange. So for example, 2, 3, 4, 5.
Okay, I get it.
Make sense?
Mhm.
Okay, good.
Wait,
Yeah.
if, about the Gilbreth permutations.
Mhm.
If J were equal to 3,
Yeah.
then can there be blocks of 3 consecutive numbers? Like here in the example, you're showing J equal to 2.
Uh,
Right.
no, so this example, the bottom row is a rearrangement of the top row. And in the bottom row, if you take J equals 3, the top 3 cards now are labeled 3, 2, 4.
Yeah.
Okay. And those are consecutive numbers, right? 2, 3, and 4.
Yes.
Does
If
this
this
not
was a
apply
5,
backwards?
though, it wouldn't work, right? Then I'd have 3, 2, 5 as the top 3 cards, and those cannot be rearranged to form a consecutive block.
And what if we take J equal to, say, 5? It would still work because 3, 2,
That's
4, 5, 1.
exactly. So this is a Gilbreth permutation. For any, no matter how many cards you take off the top, they form a consecutive block.
I have a question.
Yeah.
Um, do they also work backwards? Like, say you considered 1 and 6 consecutive since they're both at the ends. Like, they kind of overflow to
Um,
each other. Do they ever use that, or?
I don't think so. I think that might be a coincidence here,
Okay.
but you can think about it. Actually, what we're going to be interested in is not reading this backwards, but interchanging the top and the bottom. So that's called the inverse of a permutation. So if you have a permutation sigma, its inverse is like this. I'll just show you an example. So here's the permutation we had before. I just basically swap the top and the bottom, which means instead of 1 mapping to 3, now 3 maps to 1. So in other words, 3 is going to go to 1, 2 to 2, 4 to 3, 5 to 4, 1 to 5, 6 to 6, and that gives a new function. Now this is not a Gilbreth permutation on the bottom, but has a different property. So this bottom permutation sigma inverse is what we call unimodal, which means in sigma inverse, the second row, the numbers go down. So we have 5, 2, 1, and then they start going up again, 3, 4, 6. So it starts decreasing, hits a valley, and then increases the rest of the way. So permutations like that are called unimodal. And the theorem, which you can try to prove, is that a permutation is unimodal if and only if its inverse permutation is Gilbreth. So Gilbreth permutations are the ones that come from Gilbreth shuffles, and they're the inverses of these permutations that go down and then come up. So it's already some pretty interesting but fairly classical mathematics. And all those things, if you think about it hard enough, you should be able to convince yourself of. Now, to motivate the problem that I want to actually discuss, the actual math problem that we thought about, we want to think about permutations in a different way. So there's another way to write down a permutation called its cycle decomposition. So again, I think it's best done by example. So here's a Gilbreth permutation. And right, we can see that it has that property that I mentioned about consecutive runs. The cycle decomposition is you track orbits of elements under the function. So what I mean is 1 maps to 3, if you look at the first column. And then where does 3 go? 3 goes to 4. Where does 4 go? It goes to 5, and then 5 goes back to 1. And so we write that as 1 goes to 3, goes to 4, goes to 5, which goes back to 1. And in this permutation, 2 is a fixed point. 2 goes to 2, and 6 goes to 6. And you write those like that. So this is called cycle notation, and it reveals different things about the structure of the permutation than the two-line notation does. So you can see here that 2 and 6 are fixed, whereas 1, 3, 4, and 5 move in a cycle. Here's another example. 1 goes to 4, which goes to 2, which goes to 3, which goes to 5, which goes to 6, which goes to 1. So this is a 6 cycle. It's a purely cyclic thing that goes through a cycle and then comes back to where you started. So the second permutation is called a cyclic permutation because there's a single cycle. And we'll be interested in cyclic permutations. Let me know if anything is not clear. So this second example is actually both cyclic and Gilbreth. All right, so here's a lemma. Again, probably something you can prove, though maybe this is slightly harder than the previous exercises. The number of Gilbreth permutations of 1 through n is 2 to the n minus 1. And the number of cyclic permutations is n minus 1 factorial. Of course, the number of all permutations is n factorial, which I think most of you probably know. So the question I want to look at is how many permutations are both cyclic and Gilbreth? Now, this isn't exactly motivated by a specific magic trick because, you can make lots of magic tricks out of cyclic permutations and you can make magic tricks out of Gilbreth permutations. It's a little harder to think of why you would need both, but it's a natural math question. And it turns out to be quite tricky to count these. It's much harder than counting them individually. But the answer is known. And if you read the literature, you'll find there's a theorem. It's been rediscovered by different people, but the first reference I know is Weiss and Rogers. Number of cyclic unimodal permutations of 1 through n, or the number of cyclic Gilbreth permutations, if you like, it's the same count, is this number gamma n, which has a pretty complicated looking form. So it's a sum over odd divisors of n. There's a 1 over 2n out front. And then you sum over odd divisors of n, 2 to the n over m. And then there's a coefficient here called the Mobius function of m, which is either 0, 1, or minus 1, depending on what m is. So although we won't really need it for the talk, I'll show you this is what the sequence looks like. So for example, with 5 cards, the number of cyclic unimodal permutations is 3, or cyclic Gilbreth permutations. There's 3 of them. With 6 cards, there's 5 of them. 7 cards, there's 9, etc. Just for completeness, I'll show you what the Mobius function is, but we don't really need to know this. It takes 1 to 1, and then the other values depend on the prime factorization of n. So if n factors like this into primes, then if n is divisible by the square of a prime, the Mobius function is 0. And if not, then it just is minus 1 to the k, where k is the number of prime factors. And the reason this is a useful function in math, and the reason it shows up in the counting formula, is because of the so-called Mobius inversion formula, which says that for basically any functions f and g, f is the sum over all divisors of n of g, if and only if g is the sum of divisors of n of f, but with this twist thrown in where you have the Mobius function out front. And this is a fancy version of the inclusion-exclusion principle for counting. But that's not really the focus of my talk. I just wanted to show you that if you've never seen it, it's a cool function and a cool formula. But the point is this naturally comes up when you want to solve the counting problem we've introduced. And now what I want to do is show you that this kind of counting formula shows up in totally different and unexpected places as well. And I want to show you how it shows up in connection with the famous Mandelbrot set. And then what we're going to do is ask, is this just a coincidence? Or is there some reason that the same formula is showing up in two different places? Okay. So I imagine you've all seen this picture. You may not know what it means, though. So I'm going to explain that now. So the Mandelbrot set is a subset of the complex numbers. So these are things that have a real and an imaginary part. We can graph complex numbers in the plane using the real and imaginary part. And the Mandelbrot set are those complex numbers which stay such that 0 stays bounded under iteration of z squared plus c. So what does that mean? You just repeatedly square and add c, and then square again and add c, and you keep going, starting with z equals 0. And what you want to know is, does that sequence of iterates stay bounded, or does it escape out to infinity? So here's an example. If you start with 0, and your polynomial is z squared plus 1, so this is c equals 1. Square and add 1, and you get 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 5 squared plus 1 is 26. And it's pretty clear that this sequence just keeps growing and growing. So c equals 1 is not in the Mandelbrot set. Okay? But suppose you take c equals I, which is the square root of -1. 0 squared plus I is I. I squared plus I is -1 plus I. If you square that and add I, it's a little exercise to see that you get -I, and you square that. Now you're back to -1 plus I again, and you get in a little loop. So you go from here to here, back to here, back to here. You're in a 2 cycle now. You just keep going back and forth between -1 plus I and -I. So this will stay bounded. And so I does lie in the Mandelbrot set. So you can do this for every complex number C. It's either in the Mandelbrot set or not. And when you plot it, you get this crazy fractal shape. Very, very surprising mathematical fact. And I mean, it's very complex and well studied, but there's still lots of open questions. We don't have time to go into it now, but I mean, if you zoom in, like right here, you'll see these spirals. If you zoom in here, you'll see these little baby Mandelbrot sets occurring, which look very similar to the original Mandelbrot set, but like rotated and at a smaller scale. Over here on this boundary part, you see some like seahorses. They call this the Seahorse Valley. There's something else near this cusp of the cardioid, which is looks like elephants. If you look at their trunks right here. So it's really crazy that this complex structure emerges from such a simple mathematical rule. And I encourage you to watch a YouTube video. You can find these very easily, where you're like zooming in on different parts of the Mandelbrot set. It's just like watching a movie. It's very trippy. Okay, but we want to get back to like precise math statements. So let me tell you about some special points in the Mandelbrot set. So one way of being bounded is to just be purely periodic. Namely, 0 falls into a periodic cycle of length n when you iterate. That's the very simplest kind of bounded behavior, is that you're actually just a cycle. And the complex numbers with that property are the roots of a certain polynomial called the nth Gleason polynomial. Now, where does the polynomial come from? I mean, it's very easy to see. Well, just as an example, if you start with c equals -1 and you iterate, 0 goes to -1, and then -1 squared minus 1 is 0 again, right? So 0 belongs to a 2 cycle. So these are called hyperbolic centers, and they're in the Mandelbrot set. So how do you get G2, for example? Well, you just take z squared plus c. Well, sorry, it's the condition that c squared plus c, which is the second iterate, should be equal to 0, which was the thing you started with. But then you want it to have exact period too. So you have to divide by the first Gleason polynomial because those have period 1, not period 2. And so you get c squared plus c divided by c. Anyway, it's not so important that you know the details, just that these hyperbolic centers are roots of certain nice polynomials, which you can calculate. Okay, and this is what they look like. All
So
right. Yeah, question.
so the nth Gleason polynomial, it has the first n hyperbolic centers as roots.
So it has the hyperbolic centers of exact period n as its roots.
Oh, okay.
Okay,
So if
so
there
you
are
solve
x,
this. What's that?
so if there are x such centers with period n, then the Gleason polynomial only has x roots.
Correct. Okay, so the fourth Gleason polynomial turns out to have 6 roots. There are going to be 6 different complex numbers such that 0 forms a 6 cycle under z squared plus c. Okay? And there's a simple rule, recursive rule for finding these polynomials. Okay. Now, these hyperbolic centers are very interesting points in the Mandelbrot set. You can sort of see them. Like the first hyperbolic center is 0, which is here. The second one is here. There's 3 hyperbolic centers of period 3. One is at the top, one's at the bottom, and one's over here to the left. And then there's 5 of period 4. Okay. And there's some sort of rules to this, but, or sorry, I guess there's 6 of period 4. But I don't want to get into the geometry of this too much. Instead, let me tell you a few things about the situation. So it's known that the Mandelbrot set is connected. That's a deep theorem. One of the main open questions about it is whether it's what's called locally connected. I'm not going to define that, but it is related, among other things, to these hyperbolic centers. So it's conjectured that each so-called hyperbolic component of the Mandelbrot set contains a unique hyperbolic center. And this, if one could prove that, it would solve this famous open problem. So hyperbolic centers are quite important. Now here's just some interesting other things you might be interested in knowing. It's an open problem to show that the nth Gleason polynomial is irreducible for all n. So that means it can't be factored in a non-trivial way with, using just integer or rational coefficients. I've never seen this published or written down anywhere, but I did some computations and I would conjecture that the coefficients form a unimodal sequence. Namely, they go up and then they go down. But yeah, that's a little different from the unimodal permutations that we're talking about. But you can see, like here, the coefficients are 1, 3, 3, 3, 2, 1. So they sort of go up and then come down. And here's G sub 5. And again, you can see the coefficients increase until they hit some maximum, which is 116, and then they go down again. This is another open problem. All right, but I want to talk about a remarkable observation from, I don't know, somewhere between 5 and 10 years ago now, due to Booth, Floyd, Koch, and Parry. They proved that the number of real roots of the nth Gleason polynomial is equal to the number of factors of that polynomial when you reduce the coefficients modulo 2. So what does that mean? So look at the bottom one first. G sub 4, it's not hard to see that it has two real roots using just calculus arguments. And then mod 2, it turns out that it factors like this: c to the fourth plus c plus 1 times c squared plus c plus 1. It doesn't literally factor without taking mod 2, but it does factor mod 2, right? So it's conjectured to be irreducible over the integers, but when you're allowed to set odds all equal to 1 and evens all equal to 0, it factors. Whereas for G3, it doesn't factor even mod 2, and it also only has one real root. So they actually proved this very interesting theorem. And this is surprising because it's rare to see a relationship between roots over the real numbers and roots modulo some prime. So I found this quite interesting. And the way they proved it was actually they just counted both quantities and proved they were the same. And it turns out that in both cases, the answer is the same number we saw before in connection with our cyclic Gilbreth permutations, namely gamma n. So this same sequence of numbers gamma n has now shown up in sort of three different ways in this talk. And for the rest of the talk, I'm going to try to explain how they're actually connected. So when I was a mentor for the 2024 PROMYS summer program, I proposed this as a problem to try to find explicit one-to-one correspondences between real hyperbolic centers, irreducible factors of these polynomials modulo 2, and cyclic Gilbreth permutations. Like, there should be a reason that the numbers are all the same. It shouldn't just be an accident. Maybe there's like a way to make them correspond to one another. Okay, and this is what we did. So we actually made this work, and the key thing that we introduced that made all the connections between these apparently different things is something called combinatorial necklaces. So let me explain that next. So a binary necklace of length n is just a binary string, so a string of zeros and ones, but only up to cyclic shifting. So imagine putting beads of two colors together into a circular necklace, and you can rotate the necklace, and it's still the same necklace. So for example, 0, 1, 1, 0, 0, if I left shift by 1 is 1, 1, 0, 0, 0. So those two strings correspond to the same necklace, right? They're just rotationally different from each other. So formally speaking, a necklace is an equivalence class of binary strings. And now there's something called a primitive necklace, which means that if you rotate it, you never get the same string back. So 0, 1, 0, 1 is not primitive because if I rotate by 2, I get 0, 1, 0, 1 back. In other words, it consists of a repeating subpattern, repeating subword. So primitive just means it's not composed of a repeated substring. And the last notion we need is that there's an inversion map on strings or on necklaces, which just swaps 0 and 1. So if you want to think in terms of necklaces and beads, say you have red beads and black beads, and you swap colors to get a new necklace. So 0, 0, 0, 0, 1 and 1, 1, 0, 1, 1, I claim represent the same inversion class of necklaces, because if I invert 0, 0, 0, 0, 1, I get 1, 1, 1, 1, 0, and I can rotate that or cyclically shift it to get 1, 1, 0, 1, 1. So it's a different equivalence class on strings. And here's our main theorem. So for each positive integer n, there are explicit bijections or one-to-one correspondences between the following sets, all of which are known to have cardinality gamma n. First, the real hyperbolic centers. Second, the irreducible factors of Gn mod 2. Third, the cyclic unimodal permutations or cyclic Gilbreth permutations. And then we also have the primitive binary necklaces of length n, which have an odd number of ones. Those are also counted by the same sequence gamma n. And then there's a funny one. This is our main technical contribution, I think, is to look at binary necklaces that are either primitive of length n and have an even number of ones, or they're not primitive. They come from duplicating something primitive of length n over 2, repeating it 2 times, and the substring has an odd number of ones. So again, not totally mandatory that you absorb the exact definition and remember it, but it's just some concrete class of necklaces you can look at. And then there's one more, which are the inversion classes of necklaces. So where you consider two things the same, if you can rotate and swap colors to get from one to the other. So here's 6 different sets one can define. All 6 sets have cardinality gamma n. And not only that, but we have explicit ways of lining these things up so that given a necklace, I can associate a hyperbolic center and a unimodal permutation and all of that. All right, so I have about 15 minutes left, and I'm going to just give you some hints about how this is proved. The details are too complicated for a talk like this, but hopefully this looks very mysterious and unlikely, and I'm going to sort of at least give you some hints that there is some structure underlying all of this. Any questions before I sketch the proofs, though? Okay. So, just as an example, when n is 4, okay, remember G4 was a degree 6 polynomial, but only has 2 real roots. The other roots are complex. Modulo 2, I already showed you this factorization. It breaks up as a product of a quartic and a quadratic. There are exactly 2 cyclic unimodal permutations of 1 through 4, 1, 4, 3, 2, and 1, 4, 2, 3. And their inverses are Gilbreth permutations, which come from shuffles like we did in the magic trick. The set of these odd primitive necklaces with an odd number of ones is these 2 guys. That creates bar, then the inversion classes turn out to be these 2.
Uh, uh, you you froze for a few seconds, so can you go back a bit?
Oh, sure. Where did I start freezing?
You froze at P1, I think.
Oh, I see. Okay. Sorry. So P1, those are the cyclic unimodal permutations. So there's 2 of those. And then the rest are just the different kinds of primitive binary necklaces. So N1 has an odd number of ones and is primitive. N2, the one on the left is primitive with an even number of ones. The one on the right is not primitive, but has an even number of ones, and it's a concatenation of 2 substrings, each of which have an odd number of ones. And the last set, these are the primitive binary necklaces up to both inversion and rotation. And there's 2 equivalence classes here.
I have a question.
Yeah.
How did you find the relationship between n1, n2, and n3, and the Weiss-Rogers function, the Weiss-Rogers function. Like, how did you see that?
So like how do we know to look at these necklaces?
Mm-hmm.
Yeah, I mean, it was a lot of like experimentation. I mean, there were a lot of hints in the literature about what to do. Some of these things had already been connected to each other in non-obvious ways, but there was still like a missing link here.
Okay.
And I would say the missing links were N2 and N3, these last two. So basically, it was already known by various works. I mean, it's hard to dig out of the literature because nobody quite says it in this way. But the first four things were sort of, oh, sorry. Well, the first two were known to have the same size, but they hadn't been explicitly connected. But like M1 and P1 and N1, it was already known how to give one-to-one correspondences between them. So we kind of filled in the missing links. And the key was to look at N2 and N3. And it just came from reading the literature carefully and experimenting and trying to find things that work.
Okay. Thank you.
Yeah. So similarly, here's the list. I'm not going to go through it carefully this time, but here's the similar list for n equals 5. There's 3 of each thing, right? There's 3 hyperbolic centers that are real. This polynomial factors into 3 factors mod 2. There's 3 of these cyclic Gilbreth permutations and 3 of each of these kind of necklaces.
What was the exact function called again? Gamma n. I know it was like buff at top, but I don't remember the name.
Well, gamma n, I don't think it has a name. It's just a sequence of numbers.
Someone mentioned earlier like Weiss-Rogers function or something
I think
similar.
it's a
Yeah.
theorem.
So Weiss-Rogers were the first ones to prove that M1, the real roots, these hyperbolic centers, that there's gamma n of them. And Booth, Koch, Floyd, and Parry showed that M1 and M2 have the same size. Oh, sorry. It was actually what Weiss-Rogers studied was P1, but I think they pointed out that it's related to M1. And then someone else kind of made that precise. So like I said, it was very hard to find all the relevant literature here and piece it together, but a lot of these things were known. But there really was a new ingredient needed. Okay. So let me just, I don't have time to go through all the ideas. So this will be very impressionistic. So there's a famous paper of Milner and Thurston, both Fields Medal winners, on something called kneading theory, which they used to study Mandelbrot set and other dynamical systems. And this kind of explains the relationship between the hyperbolic centers and the cyclic unimodal permutations. And so it basically works like this. So what you do is for each hyperbolic center, C, you compute its iterates and you place them in numerical order. So for example, if C is this particular real number, and you track the orbit, I should have said well, you can either track the orbit of 0 or the orbit of C, because C is what you get after you apply the polynomial once to 0. So it's basically equivalent. But anyway, start with C, let's say, and then apply Z squared plus C, and you go all the way over here to the right. And then if you apply Z squared plus C again, you go to the middle. And then you go take 1 step to the left, then 2 steps to the right, and then you go back to where you started. So it forms a 5 cycle. That's why C is a root of G sub 5. But it gives you a specific permutation, namely, right, you have 1, and then 5, and then 3, and then 2, and then 4, just writing these things in order and looking where they map to. So the dynamics of these numbers gives you a cyclic permutation. And it's a theorem that it's unimodal. Basically has to do with the fact that z squared plus c is a quadratic polynomial. And so its graph is like a parabola, right? And parabolas have this unimodal property that they go down, hit a minimum, and then go back up. And there's a unique critical point where the derivative is zero, which is the vertex of the parabola. So using some calculus ideas, you can show that permutations like this have to be both cyclic and unimodal. So that's the connection between the permutation stuff and the dynamic stuff. And that's sort of classical. Now, to go from hyperbolic centers to necklaces, that's really where the kneading theory comes out. So this is a deep insight of Milner and Thurston. You can define a sequence kappa m, where each kappa m is either plus, minus, or star, in the following way. So if the mth iterative of the critical point is positive, you write plus. If it's negative, you write negative. And if it's zero, you write star. And then you transform the sequence kappa into a sequence of zeros and ones. And the way you do that is that you assign the value 0 to star, and it's sort of recursive. If kappa is plus, then t sub m plus 1 is just tm. But if kappa is minus, t sub m plus 1 is the opposite of tm. So here's an example. So if I start with this negative value of c, and n is 5, then when you iterate 0, you get these numbers in this order. And so this guy is negative, this guy's positive, negative, and negative. And now the t sequence is like this. You start with 0, and then because you have a negative, you change the 0 to a 1. And then because the next kappa value is positive, you don't change it, so 1 stays 1. Then you have a negative, so 1 flips to 0. And then you have another negative, so the 0 flips to 1.
Can you
So
explain what FC is again?
Right. F sub c is the polynomial z squared plus c. So I'm just doing what I did at the beginning. I'm looking at the orbit of 0. So I start with 0. I apply z squared plus c. Then I apply z squared plus c to that. And then I do it again and again. And by assumption, I'm in a situation where after 5 iterates, I come back to where I started, namely 0. That's what these special values of c, these hyperbolic centers, do. And I'm telling you, there's some combinatorial rule having to do with the signs, whether these numbers are positive or negative, that gives you a t sequence out of that. In this case, it would be 0, 1, 1, 0, 1. And my claim is that if you look at the inversion class of that necklace given by the t sequence, that this gives you a map from hyperbolic centers to inversion classes of necklaces, which turns out to be a one-to-one correspondence. But the fact that it's a one-to-one correspondence is a very deep theorem of Milner and Thurston. Okay. All right, so I'm basically out of time. So let me just say where our new idea was. Okay, so I'm not going to go into the rest of the details here. There's some Galois theory, which is like advanced undergraduate level mathematics to deal with these irreducible factors mod 2. I'm not going to go into that, but I realized at some point that Galois theory allowed one to associate binary necklaces to irreducible factors mod 2. So that's where that connection comes from. Weiss and Rogers that I already mentioned, when they computed the number gamma n, they really found secretly what they did. They didn't say it this way. They really found a one-to-one correspondence between cyclic unimodal permutations and these primitive binary necklaces with an odd number of ones. That's kind of a translation of their work. And so what we needed to do was find a one-to-one correspondence between this funny set, which I was calling n tilde plus, and inversion classes of necklaces. If you can do that, it sort of ties all the other things into a big interconnected web, and you can get bijections between everything. So this was kind of the last step in the program. And it turned out there's a very simple thing that works. And I'm out of time, so let me just do this very briefly. If I start with, so the SI are the bits of my funny necklace. And all I do is I take the partial sums mod 2. So I just sum up the first I bits and then take that mod 2. And I get a new necklace that I call C of S. So C just takes one type of necklace to another. And what we managed to show is that this gives a one-to-one correspondence between these two mysterious looking types of necklaces. And that basically closed the loop and allowed us to prove the theorem. So with that, let me see if there's any questions.
Yeah, thanks for a great talk. And yeah, students, are there any questions?
Um, what is like the motivation for defining such a function, if I may?
Sorry, I wasn't able to hear the question.
Um, what's like the motivation for like defining C?
Oh, for defining C?
Yes.
I mean, we just wanted, we knew that these two kinds of necklaces had the same counting function. So we suspected that there was some way to transform one type to the other. And this is just what worked. This was actually the PROMYS students' discovery. I mean, I think they just tried things and this ended up working. It's natural in retrospect when you understand the kneading theory well, it has some kind of interpretation. It's basically like a cumulative count of negations. Like you're applying some polynomial whose graph is a parabola, and so the derivative, like whether you're increasing or decreasing on the next iterate depends on whether you're positive or negative. And yet this is like keeping a cumulative total of the number of times that you decrease rather than increase, or something like that. So I mean, there is some kind of intuition behind this, but I think the students found it just by trial and error.
Okay, thank you.
I did want to kind of ask basically my interpretation of the cyclic necklace or like primitive necklaces
Yeah.
because I'm pretty sure n bar counts the even primitive necklaces or
No, actually, even primitive necklaces don't really appear here. You have to modify the even ones. N bar is these inversion classes, meaning that you can now consider two necklaces equivalent if they differ by a sequence of rotations and inversions where you swap 0 and 1. And this
what
counts how many inequivalent necklaces there are.
what was n tilde? Was that even?
Yeah, so n tilde were basically the even primitive necklaces, but you have to add in some non-primitive ones as well. So you have to add in the non-primitive ones, which come from repeating two primitive guys of length n over 2, each of which have an odd number of ones.
Uh, yeah, so the reason I wanted to ask about C or this function basically
Yeah.
was this is similar to like if you take a binary string and
Mhm.
then you XOR adjacent bits
Yes.
um, throughout the entire thing, it's the same as just add. I'm pretty sure it's the same as adding everything and taking the sum mod 2.
Correct.
So
Yep.
the reason I kind of wanted because I'm trying to figure out somewhat what the motivation was because of primitive strings.
Mhm.
Uh, I think if you take for the nth index in the string, if you take basically the XOR sum until that index, and then
Mhm.
like replace that index with the XOR sum, then based on some operation with all of those bits, you get the answer to whether it's primitive or not. I was just like trying to figure this out. So I wanted to ask, does this kind of have any motivation to do with why you're, adding everything and taking it mod 2? Because it's kind of a connection there.
I guess so. But I mean, I think it's really not obvious. Like I just stated this theorem, I didn't talk about how you prove it. Um, I mean, it really, you have to do a bit of analysis here to see why. I mean, even the fact that it's well defined requires a proof because um, I've defined it on the level of strings, but you have to show it doesn't depend on the necklace, meaning if you rotate the sequence S, you get the same answer. And you also have to really check that the right-hand side here, the n bar, these are all primitive, but the left-hand side can have some non-primitive things. And you have to check that these conditions all line up. And it's a bit technical, so I don't know how to summarize in a simple way kind of why this works, but it's sort of a basic principle that this works out.
So there's not like a specific motivation you can tie the function C to.
I mean, like I said, I think it's very natural to consider partial sums mod 2. Like you said, it's kind of related to XOR. I mean, it's a common operation to do with strings. Um, so it's a natural thing to try, but the theorem that this is really well defined and gives a one-to-one correspondence is not so trivial. And I can't really give so much intuition as to why it works. Just you kind of go through the proof and there's different cases and it turns out to work.
All right, thank you.
I just wanted to ask one question.
Yeah.
Going back to the function where you define like the z squared plus c, I
Mhm.
was just kind of confused. How'd you connect that back over to the primitive sequences and the non-primitive ones?
Ah. Um, okay, so if you have the z squared plus c, right? In this picture here, you get a cyclic unimodal permutation from that. And now the connection to primitive sequences is through this kneading theory. So the way to get a inversion, a primitive, I mean, N3, I should have written inversion classes of primitive necklaces. So this kneading construction will give you automatically a primitive sequence. But the proof that it is primitive is not so straightforward, I think. I mean, so the kneading sequence you define in terms of these sequence of pluses or minuses, and then you do this T transformation. And the theorem is that you always get a primitive necklace from this construction if you start with a C of exact period n. But I think it's not so intuitively clear why that works, and it's certainly not clear why that's one-to-one correspondence.
Yeah, it's kind of just what I was wondering. Like, did you guys ever make like a formal proof about that part, or is it kind of just assumption?
Well, we have proofs of everything in our paper. This is just a talk where I'm giving ideas. We have a paper on the archive that's actually been published in a journal now, and you can find it online. I can send a link to Simon. But so we have proofs of all of these things. But this particular fact that the kneading transformations here give you a primitive necklace is kind of implicit in this paper of Milner and Thurston. So I wouldn't really call that our theorem. All we did was explain how the work of Milner and Thurston implies this formulation of the result, but kind of the key ideas are already in their paper.
Okay, thank you.
Yeah, speaking of the paper, could you like put the link in the chat if possible?
Sure.
Thank you.
I'll do that right now.
Or the title would be.
Yeah. It is, I'll post the link in just a second, but it's called Necklaces, Permutations, and Periodic Critical Orbits for Quadratic Polynomials. So let me, wait, where did the chat go? Sorry, it disappeared from my screen because I minimized something. Okay, here we are. There's an archive link.
Brilliant. Thank
Any other questions?
Okay. If there are no more questions, then thank you again. And then we'll move on to the next to the class. So let me end the recording here.